In years gone by, cyclists who found their transport hard work would go to almost any length to make things easier. Some just wanted life to be a little softer. Others never did completely trust the wheel and would rather use their feet, or preferably somebody else's. And there were those who found the work so thirsty they couldn't bear to be far from the nearest beer. But finally, in 1902, came an invention which helped every cyclist to surprising achievements. Sir Frank Bowden, cycling pioneer and owner of a small bicycle company in Raleigh Street, Nottingham, had realised that a variable gear would make cycling so much easier and far more popular. Approached by Henry Sturmey and James Archer, who had been working on 3-speed gears, he combined their two inventions and produced the world's first reliable 3-speed hub. It was an immediate success, and in the years that followed, the range increased and thousands of refinements were made. Sturmey-Archer hubs were fitted to millions of bicycles throughout the world as cyclists realized the benefits of enclosed gearing, protection from the elements, reliability, ease of operation, and low maintenance. Today's hubs are still setting new standards, produced to the highest levels of quality using the very latest computer-controlled technology. Every Sturmey-Archer hub from the very first has been based on the same engineering principle. It was the invention of James Watt, the Scot who also developed the steam engine. And like all good ideas, it's both simple and elegant. Imagine pushing a beam across a roller which rotates freely on a pin. The beam moves easily over the roller, and a point on its surface will move as far from left to right as a point on the surface of the roller moves around its circumference. Now, if the roller were allowed to move across the floor as the beam were pushed, the point marked on the beam would travel further in a left to right direction than before, by as much as the roller moved in the same direction. As a first step in making this knowledge work for us, let us give the floor, the roller, and the beam teeth to prevent them slipping. If this simple machine is then made to operate in a circle, we have the basis for a usable system of gears. We must start by naming the components of this system. The fixed floor has now become a fixed pinion, the sun pinion. Revolving round it, the roller becomes a planet pinion. It still has a pin through it which is fixed to and rotates with the planet cage. Finally, the beam becomes the gear ring. If we apply power to the planet cage and move it through 90 degrees, the additional rotation of the planet pinion causes the gearing to move further. In this instance, an extra 30 degrees, making a total of 120 degrees. Conversely, if the gearing is rotated 120 degrees, the planet cage moves the planet pinion through 90 degrees. In other words, our simple system of gears gives the ratio 120 to 90, or 4 to 3. The Sturmey-Archer system applies this basic principle in a bicycle hub. Power is introduced via a sprocket, revolved of course by the chain. If the sprocket could be made to turn the planet cage, and the gearing were connected to the hub, we would have high gear selected, with the hub rotating 4 times for every 3 rotations of the sprocket. If the sprocket were connected to the gearing and the planet cage turned the hub, we would have low gear, with the hub turning 3 times for every 4 rotations of the sprocket. And if the sprocket could be made to turn the hub directly without passing the power through both planet cage and gearing, we would have normal or second gear. This is the basis for the 3-speed bicycle hub. In practice, of course, more components are needed to make a hub work effectively. Firstly, there are additional planet pinions attached to the planet cage, and the drive from the sprocket is transmitted via a cross-shaped clutch. Connection from the gearing to the hub is made via pawls fixed to the ring. These engage with ratchet teeth on the inside of the hub shell. Likewise, the planet cage can be linked to the hub shell via pawls fixed to its outer surface. In high gear, the clutch is allowed to engage with the planet pinion pins, giving a direct link from sprocket to planet cage. As the planet cage turns, the planet pinions rotate, turning the gearing faster. The gearing pawls, engaged with the hub ratchet teeth, then drive the hub. The planet cage pawls are overrun because the hub is moving faster than the planet cage to which they're attached. In cutaway, the mechanism becomes clear. With the gear lever in position 3, the clutch spring is fully extended, pushing the clutch into the innermost position. The sprocket is attached to a driver which pushes against the clutch arms. They in turn engage with the planet pinion pins, which are set into the planet cage, and therefore make it turn. As it does so, the planet pinions rotate about the sun pinion and cause the gearing to rotate at a faster speed than the planet cage. The gearing pawls attached to the gearing then locate in the hub ratchet teeth, and the drive is thus transferred to the hub itself. By selecting position 2, normal gear or direct drive, and altering the position of the clutch arms avoid the planet pinion pins when they rotate, but engage with the gearing splines. This effectively transfers power directly from the sprocket via the gearing pawls and hub shell ratchet teeth to the hub. In cutaway, the drivetrain is evident, from the sprocket through the driver to the clutch, which is seen here in its intermediate position, to the gearing splines and thence through the gearing pawls and the hub shell ratchet teeth to the hub itself. So in this case, the hub will rotate at the same speed as the sprocket, and as in the previous example, the planet cage pawls are overrun by the hub ratchet teeth because the hub is turning faster than the planet cage. In low gear with gear position 1 selected, the clutch still engages with the gearing splines. This connects the sprocket to the gearing, but the clutch is now positioned so that its arms also deflect the gearing pawls and prevent them from engaging with the ratchet teeth on the hub. As the gearing turns, the planet pinions turn the planet cage at a slower rate. With the gearing pawls deflected, the planet cage pawls can engage with the hub shell ratchet teeth and drive the hub. In cutaway, the drivetrain can be seen passing from the sprocket through the driver to the clutch, which is in its outermost position. The clutch arms both deflect the gearing pawls and engage with the gearing splines to transfer the drive to the ring itself. From there, the planet pinions turn the planet cage and allow the planet cage pawls to engage the hub ratchet teeth. More than 80 million Sturmey-Archer hubs based on the epicyclic gearing principle have now been fitted to bicycles all over the world. With an increase of more than 1 million hubs per year, every cycle engineer should know the necessary service techniques of hub disassembly, component checking and reassembly.